Hey guys, how are you doing? I hope that in these challenging times you are doing pretty well. I am Indy Nazmul Hassan, the founder of Tensorbundle. You will know me more or less. I have been trying to reconnect you with the group members to share our knowledge on antenna engineering, and this is the purpose of arranging this webinar. Today we're going to learn from industry speaker resource person about the phased array system in HFSS. And uh, I hope that this webinar will give you some hands-on experience on designing the phased array in HFSS. I also believe that by arranging these types of seminars regularly in this group will strengthen our networking and also our professional bond by sharing our mutual knowledge with one another. So without much further ado, let's begin our main session. So I am inviting Njas from ANSYS Incorporation. He's working as a senior application engineer right there. So hello, Njas, how are you?
I'm fine, Hassan. Doing great.
Okay, so I'd like to request you to introduce yourself briefly, and then maybe we can start the main session.
Yeah. Hi, team. So my name is Njas. I'm working as an senior application engineer in ANSYS, supporting on or working on antennas, antenna array, radars, 5G MIMO systems, those kind of areas. So my industry experience in such a way that the people who are designing the defense systems, people who are designing the antenna for IoT applications, 5G MIMO based base station antenna. So connecting with these people, and if they are facing some challenges in terms of solving the problems, getting some issues on the technical side, supporting those customers across the India and sometimes globally also. And today we were planning to have a short meeting on phased array system that can be extended for 5G applications. So this is talking about how to do a physical channel simulations. So 5G, you know that there are different frequency bands are allotted for 5G applications. One is sub 6 gigahertz gigahertz frequency band. Less than 6 gigahertz are mainly using for mobile voice over mobile internet on the mobile, something like what we have currently for 3G and 4G. Okay, but there are some high frequency band also allotted. Those are called 28 gigahertz are main, and then 60 gigahertz are the other one. So there are some limitation if you go with higher and high frequency. The advantage is you are getting very wide band. Your data rate will be so high. You can transfer the data like within seconds. The problem that at a higher frequency RF losses are very high. So if you want to transmit some, if you have a base station at 28 gigahertz, assume that at outside, you need to have such base station every 250-meter away to have a good communication. After 250-meter, the signal reduction is too much. Your system will not have that much speed up. So assume that situation at 28 every 250-meter you have a array base stations, and at 60 gigahertz what happening is there is a oxygen molecule absorption happening at that frequency. So it cannot be used for external. So 60 gigahertz mainly people are trying to include in the indoor Wi-Fi kind of a wireless access points. So we are going to cover that 28 and 60 gigahertz. So this is what it do in the 5G. 5G, wherever the user equipment goes, assume this is a user equipment. So wherever you go, your base station beam will follow you. Okay. So this works perfectly fine if you don't have any blockage between the user equipment and line of sight. Okay, the base station. The moment if you have some kind of a blockage, assume these two are metal and this is a user equipment. The moment your the line of sight is blocked, your base station will scan for another alternate path. So this is called adaptive beamforming. It will keep on checking your status, and moment you have some kind of a blockage, it will change the things. Okay, so here we are going to discuss two cases. One is for outdoor simulation, one for indoor simulation. This is for 28 gigahertz, and this is for 60 gigahertz simulations. Okay, we'll go a little bit on the 5G scenario simulations kind of thing. Okay, so before going into 5G scenario simulation, we have seen in the earlier presentations, most of the simulations are taking like 200, 300, up to 400 GBs. And assume if you want to simulate in a large city kind of an environment, this then the requirement will be too high, right? So there the advantage of other solvers comes. So you solve your antenna with the FEM, and you simulate the scenario with SBR kind of solver. Okay, SBR is nothing but shooting bouncing ray techniques. It will shoot the rays across the boundary. I will just show you a quick animation here. So assume this is my city. I can import the city model into the tool and assign the material property of each models. And then I can place my simulated antenna on top of the point where I need it. So I can even place the base station. I can place the user equipments. So this is a one user equipment, which is a mobile device, and the building on top of the building, I have a base station antenna, which is simulated already. Okay, and what SBR will do is, if you see the animation, it will shoot the rays to the entire area and paint the current because of that incident. So depends on the material property, the micro signal will be reflected back and forth between different multipath. It will paint the current due to each multipath, and you can see this is a current which is painted with respect to different bounces in the SBR simulations. Once these bounces are started, what will happen, this can, if there is a line of sight happening, all the current can receive to the receiving antenna. So it actually calculating the receiving the S21 between the antenna. This can be used for the SBR plus kind of solver, can be used for SBR coupling between the antenna. Second one is antenna placement analysis. If you have an antenna which you designed for aircraft or ship, the moment you keep that antenna on a ship or aircraft, because of the metal structure nearby, the pattern going to be completely going to change. Okay, you will be able to see because of that how much is the variation in the radiation pattern. And another application of SBR is a radar cross-section RCS analysis. You can, within like a fraction of minutes to an hour, you can simulate RCS of a big ships and other thing. Okay, so let's go with a massive MIMO. So you have a very n number of antenna array over here. You have a user equipment. What in the practically what mobile device will do is, they will send a pilot signal. Okay, they will send a pilot signal to the base station, and it is nothing but it's you are trying to calculate what is the magnitude and phase, which is going to, mainly the phase is the one which plays how much is a phase from this mobile to the antenna element of the array, and from this mobile to the antenna element of the array. Okay, once you calculate the phase, that is called channel state information. Okay, so you are capturing the channel state information with the complete scenario. With your city, you are simulating the complete scenario. It includes your multipath. Once your simulation done, you what you can do is, now I know what is the phase difference between this mobile to the each elements in my antenna array, and this element, this mobile to this, what is elements phase between the antenna elements. Then I can take the inverse of that. So what it will happen in the actual scenario is, it will direct the beam towards this particular users rather than radiating to the other one. Okay, so this is this technique called maximum ratio transmission algorithm. You are taking the channel state information and then do the inverse of that. There are other algorithm also. It's called a zero force beaming algorithm. What it do is, always in communication system, interference is the one which degrade the data rate. Okay, so let's assume I have a base station, I have a user equipment which I need to have a proper communication. But if I have something like an interfering user equipment, this algorithm what it will do is it will identify where the interfering user equipment, it will try to reduce the radiation towards that, so that even though this is radiating, the it is not going to affect the performance of this one. So you are getting a good signal to noise ratio, and uh, mm, you are susceptible to the interference created by this system. That's the advantage with this algorithm going to give you. So this is the you will get pretty good literature or data on these two algorithms. Uh, Coming back to the scenario simulations. So what you can see is then a portion of a city, and over here you can see a base station placed on top of a building, and multiple vehicles are there. Each vehicles are equipped with a vehicle to vehicle communication antennas and other thing. So we are going to see if the vehicles are moving here and there, how the spatial distribution of the array system is trying to radiate towards different uses. Okay, so you can see this is the top view of that same city. So you have a the base station here, your vehicles are moving in different directions. And what you are going to see in the next one is you are going to see the UV space of the UV radiation space of this 5 user equipment. So the beam is shifted to the 5 user equipment, and wherever these users are moving, you can see the radiation pattern also changing with respect to the users. So this using the spatial multiplexing, different part of the antennas are radiating towards a particular user, and other antennas are radiating towards the other users. Okay, so this is a one example, and you will be able to see with respect to the position. So if I'm changing the position of each vehicle, I'll be able to see what is the coupling between the base station to the user equipment or the vehicle. And you can see there are some coupling the base station to the user equipment coupling. You can see very high variations. Immediately it's going up and it's coming down. Why it is happening? It is happening because of the multipath. So if the multipath happen, what is going to happen is sometimes you will see construction of signals, sometimes you will see destruction of signals use. That's the reason you will get a peak and then coming down. So wherever you have a very good line of sight, you will get give a more or less right signals. So some signals you can see more or less right across this. Okay, and one interesting thing is if you see this green one, which is actually stopping at this point, and the moment it stops, you can see this coupling is also stabilized. Okay, so this is a parametric simulation. Each parametric simulation, after that it's linking with the MATLAB and trying to calculate what will be the coupling. Okay, so coming into the second scenario, which is the indoor application, this is called Wi-Fi 6. It's working at 60 gigahertz. You can see a 4x4 antenna array systems are there. And this is at 60 gigahertz, you probably know the wavelength is about 5 to 6 mm. And if you are going to simulate the entire building, that itself is a huge simulation point. And you can see there is a base station which is 4x4 array, 16 element antenna is here, and there is a user equipment. So my intention is to give a proper radiation towards this guy so that the coupling will be always good. And what will happen is when the person is moving, and he is also having a kind of a mobile device which is an interfering device for this communication. So if I slow down the simulation, you can see the moment this guy was walking, you can always see there is a null which is following with that person. So over here you can see one more time. So you can see wherever he goes, there is a null, the one which follows that particular user. So this kind of techniques in the for the 5G base station team will help to create different algorithms. So they can simulate different scenarios and use different algorithm in the background and reduce the interference and maintain increase the coupling between the base station to the user equipment. These all are some of the simulations. That's all from my side. And if you are having a questions, please feel to put your question in QA session.
Thank you, Njas. It was an excellent information sharing from your side. You discussed pretty well, comprehensively. Um, so I have one question. For example, in the first session, uh,
Okay,
could you please go back to page 9?
page 9. Okay,
Yeah,
I think better to take off
right.
this presentation. Yes, over here.
Okay. So in HFSS, is it
Mhm.
possible to analyze or to know the angle of incidence and the angle of reflection from each individual element of the array? For example, I want to know
Mhm.
at which particular angle the wave impinges any element,
Uh-huh.
and which particular way. For example, in normal electromagnetics, what happens when a wave impinges on an element, then the angle of reflection is equal to the angle of incidence, right?
Yes, yes.
But if I provide different phase angles in each port of the antenna elements in the array, for example,
Mhm.
one element should be given a different phase angle and another is different. But
Yeah,
in that case, the angle of reflection will be different from each element because their phases are different.
correct.
So how do I know that particular angle of reflection? Is it possible to know from HFSS?
Yes, it's called an active S parameter. So active S parameter will take care of that particular thing. So assume in the normal S parameter, if I am simulating, I'm going to let's assume I'm removing the complete power divider sections here. Okay.
Mm-hmm, mm-hmm,
So I have only these particular antenna elements in the simulation. So I have
mm-hmm.
port 1, port 2, port 3, port 4, assuming that simplified versions.
Yes,
And assume I'm just going to use normal S parameter and how that normal S parameter is computing. So in normal S parameter, I will assume I am exciting only the port 1 and all antennas are terminated with 50 ohm.
exactly.
Okay. But in actual array system, what happening is uh, if you're in the actual antenna system, array system, most of the antennas are working together or most of the antennas are exciting with a little bit of phase difference. So you will see normal S parameter and when the antennas are working situation, both will give you different S parameter. So to capture that one, there is a term called active S parameter. So I think I have somewhere it's mentioned. Mm, yeah, coming here. Yes, here. So this is called active S parameter, which is calculated based on this particular equation. So let's assume I have a pen. Let's take I have one antenna, I have another antenna. So the active S parameter is nothing but AS11 is nothing but the S11 of my antenna. So this is the normal S11 of antenna plus S21. So S21 is the one which is having the coupling between the port 2 to port 1. Okay. And with the e raised to j uh, 5. So this is your excitation phase.
Okay, okay.
Okay. So you're assume this is my S parameter, normal S11. Because of the coupling, because of this S21 coupling and the excitation phase, I may get a different S parameter.
Right.
So this is called active S parameter, which can directly get it from uh, HFSS.
Thank you so much.
You can reach out to me separately. I can share one good workshop material, how to do
Okay.
it in manually.
Mhm. So, a few questions from the audience. Uh,
Yes.
Kalani Mishra, she is saying that what's the feeding techniques used here?
Feeding techniques.
Yes, feeding network, maybe she's
Okay.
asking.
Okay. So this is a corporate feed, which you have seen, but there are different types of feedings. So the series feeding, corporate feeding. different types of feedings are there. So over here you can say you're exciting the port here, port to 1 with, let's assume, 16 watt. Okay, and it would divide this power into 8 watt here, 8 watt here, then it will divide to 4 watt here, 4 watt here, then it will divide to 2 watt here, 2 watt here, then it will divide to 1 watt here, 1 watt here. So if you do a literature survey on power dividers or the feed system for antenna array, you will see corporate feed, series feed, and different other feeding system. This is the corporate feeding techniques.
I see. Okay. Waze Khan is saying that how to find the combined gain of two-port MIMO antenna.
Okay, so the S parameters are nothing but as I mentioned, if I have a two antenna, you will get S11, you will get S21, you will get S22, and everything. So this one, while I'm measuring or simulating, when I'm measuring the S11 of my system, I will assume this is terminated with the load impedance, which is a 50 ohm. Okay, and when I'm simulating the other one, this will assume this is exciting, the other one is terminating with 50 ohm. So S parameters are independent of the excitation of elements. Okay, normal S parameter, active S parameter, which I explained. But in the HFSS, if you take, I think I can quickly show an example here. Where is HFSS 2020? If I open the HFSS with just a simple example, I can show you where you need to change that MIMO system. So there is an edit source in the HFSS. You can just right click on the excitation. It will open the edit source. There you can put the magnitude of excitation. You can put the what the phase of the excitation. Immediately the result will change for the gain. So it's just one simulation. Then you can change your magnitude, phase. Immediately the results will get updated. So if I quickly show this for example, you go to example, go to HFSS, go to antenna. So you can see 5G. Okay, I think I can go to extra large. I can. There is something called there is a 5G array with 77 gigahertz. There is something called simple antenna. Yeah, phased array units. No, not this guy. Not this. Yeah, this one, planar. So I am just opening one example file. Let me save that into a particular area. So Facebook HFSS group. These all are the some of the example I tried to answer, solved for some of your queries. Okay, let me try to run the simulation. Okay, it may take 1 minute. So meantime, if you have another question, I can try to answer that. So this is a place where you need to edit it.
Okay. Yeah, we have some other questions. For example, Shahif Mazumdar is asking how the amplifier is integrated into your power divider.
Okay. Okay. So as I mentioned, the amplifiers are nonlinear devices that will not hold the Maxwell equations. So you need to couple your HFSS simulation into circuit simulation. I can just quickly show an example here itself. Okay. I can just connect a inserted HFSS circuit design, click OK. Then what I will do is I can just drag and drop the HFSS design into circuit. So over here I had 5 ports, okay, on the HFSS. That 5 ports came over here, and let's assume I wanted to create a amplifier. You can see all the components are there. If you are not able to get it, just click on the show all, type amplifier. I'm sorry. Oops. If the search is, it is coming here, you can see the amplifier. If it is not able to trace it, this is, here is the list. So if you want to see diodes, diodes are so many diode models are there with pin diodes and other thing. If you want ideal microwave components, something like attenuator, circulator, coupler, gain, so you can see the gain. This is the one uh, symbol gain system. So what you can do is just keep the gain here. So I'm just keeping it. And if you click over here, you have option what is the gain of your amplifier, what is a 1 dB compression point, what is a 3 dB compression point. All these values of a amplifier can be connected. Otherwise, if you go and get a amplifier from a vendor, they will give you the amplifier as a spice file. That also can be connected here. So you can connect a port here. In the port, connect use a wire, and here you specify it has a gain of 7 dB of amplifier gain, and then run the analysis. You will get a complete system analysis. I think I can create some quick video and show you how to do it. I will post you in sometime next week on the same group how to do that one. So coming back to the second question, it was on how to combine it, right? So let's take this analysis. I have right now all the antennas are exciting here, okay? And if I do the complete radiation pattern, I just go here and putting the radiation pattern. Okay, this is for 2D, so I'll put 0 to 180. So in HFSS, most of the things are, you can say, post-processing. After the simulation, you can change everything. It will automatically update it. So this is a radiation pattern coming from all the antenna. Okay, so you can also see these antennas are radiating not exactly to the broadside because you set some kind of a phase shift. If I change the phase shift of the antenna element, this is a progressive phase shift, it will immediately change to different. This is a broadside radiation. So if I right click and show modular window, you will be able to see how the radiation going to come out from the array. So this is a way we can easily uh, put the, you can see this one. Okay, let's say I wanted to see the radiation of a one antenna element, so I can just go here and instead of other elements, all elements I put as a 0 0. Okay, now the pattern which you are going to see is for single element. 1 minute, something fishy. Antenna. Okay, some issue with the result, which you should be able to see the single antenna pattern.
But the principle is same, so we can figure it out. No problem.
Yeah,
I
yeah.
think the
Principle is same.
audience,
Yep,
yeah,
correct.
audience is smart enough to figure it out by themselves. I think so. But you explained the principle very well, so we can do that by our own. I hope so. No
Correct.
problem. Mhm, mhm. Okay. Now, coming back to the next question, layout will be in the same place. Yeah, definitely. I think so, right? Yes, layout is in the same place. We generate the 3D model inside the HFSS. I mean, he was talking about integrating the amplifier
Uh-huh.
and then generating the layout, right?
In the circuit.
For example, we need to keep a space for the PCB amplifier within the layout.
Yes, within that one where you have a amplifier, you
Mhm.
keep that space there left over there.
Exactly.
Okay, and you keep a port for input port for amplifier, output for amplifier,
Mhm.
and
Mhm.
take that into circuit and then do that one.
Right. Okay, so I think that those were the questions asked from the audience. So we can wrap up the webinar. Nijas,
Yeah,
it was really pleasing experience to have you with us, and you shared very vital information with us. I hope that this knowledge sharing will be continuing. I have a
yeah,
plan
sure.
to I have a plan to bring you again. Maybe you can talk on another topic. You are a very
Yeah,
resourceful person and having a very good command on HFSS and internet engineering. So we are very lucky to have you in our group. And
yeah. Thanks,
thank you
Hassan.
so much.
Yeah.
Mhm. Okay,
So
so
we'll catch up sometime later. Yep.
sure. And thank you, the audience, for remaining with us. We will be again in touch in another episode, in another webinar. Till then, I hope all of you are good health and keep active in our Antenna Lab group so that whenever the new webinar comes, you can get the notification. Thank you again. Thanks all. We are signing off. Nijas,
Yeah,
it was really pleasing experience to have you with us, and you shared very vital information with us. I hope that this knowledge sharing will be continuing. I have a
yeah,
plan
sure.
to I have a plan to bring you again. Maybe you can talk on another topic. You are a very
Yeah,
resourceful person and having a very good command on HFSS and internet engineering. So we are very lucky to have you in our group. And
yeah. Thanks,
thank you
Hassan.
so much.
Yeah.
Mhm. Okay,
So
so
we'll catch up sometime later. Yep.
sure. And thank you, the audience, for remaining with us. We will be again in touch in another episode, in another webinar. Till then, I hope all of you are good health and keep active in our Antenna Lab group so that whenever the new webinar comes, you can get the notification. Thank you again. Thanks all. We are signing off.